Good evening, everyone. A very warm welcome to all the participants. I'm Saryu from S. Chand Publishings. Once again, today, on 6th May, I welcome each one of you on the second day of the Maths webinar under our CPD training initiative. Today's session is in continuation to our yesterday's session. The topic of today's session is Using Stories to Teach Maths, Part 2 by Ms. Jaspreet Sethi. In yesterday's session, Jaspreet ma'am had emphasized the importance of vocabulary and correct terminology in mathematics. Also, how stories from our personal experiences play an important role in developing interest in the subject. We all hope that today's session will also be as enriching as yesterday's. So now I welcome our maths expert, Ms. Jaspreet Sethi, to continue this session. Over to you, Jaspreet ma'am.
Thank you, Saryu. Hello, everyone. As I move forward, I want to first check if my screen is going to be visible. Saryu, I'll need you to stop share.
Ma'am, you're visible and you're audible.
All right, perfect. And let me see if my presentation is visible to everybody. Maybe Saryu, you can give me a heads up.
Yes, ma'am.
All right. So this is where I will actually, we'll open the chat, Saryu, right? So today we are going to start with a game. As we started yesterday, and yesterday I had some questions after the session. Some of the teachers I know said that the game we played at the very beginning, I missed out on the name. And what's that number? I just want to reiterate. That is Kaprikar, an Indian mathematician's constant, 6,174. If you missed how you find it, you can Google it now. But we shared this yesterday at the beginning of the session, and today I like to play games, and I like the fun element going. So we're starting with a trivia. Let's see if any of you are able to guess the names of any of these mathematicians all across the globe. And if you know, then you can just write number 1 and whoever the mathematician is. And if you can please type that in the chat. As I'm asking, I'm going to probably give a minute so that everybody can kind of read through those questions. And let's have fun. Let's see if we are able to get somewhere with this, if we have any knowledge of the giants that came before us, whose shoulders we are standing on. So let's play trivia. Is the chat box open, Saryu?
Yes, ma'am.
All right, perfect. So here are my questions. They may be a little short, so I'll read them, short in font. An Indian mathematician known for his work on number theory and fractions. Anyone? You can just start typing in the chat, but you can please put 1 and then list the name if you do know. Or a Scottish mathematician who developed the logarithm, logs. I know I'm catering to K through 12. It's okay if you do not know any of these, and that's totally fine. Just for fun. German mathematician known for her contributions to abstract algebra and topology.
You started getting answers.
You started getting some responses. Yes, I'm seeing that. Awesome. I have a lot of people saying Ramanujan. Actually, no, but that's fine. And we have some names. So now people are just throwing names. Euler, no. For the Scottish mathematician, no. Persian mathematician known for his work on algebra and the quadratic equations. French mathematician known for his work on probability theory and statistics. Anyone? Chinese mathematician who is known for being ahead of his time for calculating pi accurately to about 6 decimal places. French mathematician known for her work on number theory. I have some right answers somewhere. I'll give out as I finish reading. So a lot of people are saying Napier for the second one, Sophie Germain. Yeah, actually, Alan Turing, no. For math, yes. We'll talk about that. So British mathematician known for her work on computer programming and the first computer algorithm. Anyone for 8? So now I have maybe people who do know, maybe who people have started Googling. These are my solutions, my answers. And the first mathematician to be known for his work on number theory and fractions is actually Brahmagupta. And the Scottish mathematician, I think I got a couple of right answers for 2. And I think Sophie Germain also, I think Ada Lovelace. Now I'm getting some of these responses right. I did not at any point, I am going through the chat. So pardon me if I'm looking like I'm staring, but I'm just trying to see if I got some responses for the 8th one. I don't think yes, I did see Manjushri. Thank you. That's Ada Lovelace. And I think I got format from many people. The Chinese mathematician, thank you, Shankari, that is right, is Zhu Chongzi. So good to know that we are aware of some of the mathematicians that have contributed to the maths that we know and do today. And as we play this game, it brings me into our segment today, which is our continuation on using stories to teach math. Saryu, you can close the chat. And thank you so much, everyone, for participating and being part of this. So yesterday, we spoke about language and vocab and our own stories and how our questioning techniques and real world connections and how problems we pose, which are using mathematical applications to be solved. We discussed these yesterday, and today we are moving into literature and popular culture and history of mathematics. So literature, I have to say one thing right out here again, sort of an understanding, a mutual understanding with all of our participants, that it's 60 minutes and I can only handpick a few stars in a galaxy of billion trillions. So I may not get to everything, but I will give you sources from where you may get more books and more literature, and not everything needs to be purchased. Thanks to YouTube, thanks to Read Alouds, we have a lot of them. Again, we're standing on shoulders of giants. We already have so many beautiful people who have contributed to this and have read these stories. But if you're not aware of some of them, I'm trying to pick some of my best, starting from our youngest audience. And our youngest audience are the ones who are the youngest to teach our youngest lot, which is the kindergarten. So literature and popular culture, I begin with the most beautiful story on The Very Hungry Caterpillar by Eric Carle. And I am not going to have spoilers, and I'm not going to, okay, my background may not show that. I will not go through the entire story, but I will give you the gist. So it will be sort of a spoiler because and I will talk about the math connections that the book brings, sorry. So there was it starts with an egg on a leaf, and then the egg transforms to a baby caterpillar who starts to look for some food. It's very hungry and starts to look for some food. And then on Monday, he ate through one apple, but he was still very hungry. And then on Tuesday, he eats through 2 pears, but was still hungry. And it goes on like that until on Saturday, he ate through one piece of a lot of junk. And that night, he had a stomachache. And the next day was Sunday again. And the caterpillar ate through one nice green leaf. And after that, he felt much better. So the idea is that, I mean, it shows life cycle. I'll build all the, I'll talk about all the topics that the book addresses. But as the book is reaching its climax, we have a hand raise, I think. I'm not sure, Sethi, if you could take care of that. So the small caterpillar becomes a big caterpillar, and then builds a cocoon, and then finally is a very beautiful butterfly. So some of the math concepts that this book discusses is sequencing, number sense, number recognition, one-to-one correspondence, days of the week, life cycle, addition, progression, patterning, eating healthy. A lot of these themes are taken care of in the book. And then my other beautiful book, which progresses a little bit, I would say, with second, third graders, sometimes even fourth, fifth, depending on the level of students, would be 100 Hungry Ants. We again have some hand raised. I would just say that I will be addressing questions towards the end, but if those questions are related to you not being able to hear or say anything, please get in touch with Saryu. So 100 Hungry Ants is another beautiful book. I go through very few snippets of the book. Stop, said the littlest ant, we're moving way too slow. Some food will be long gone unless we hurry up. So a little bit of background. These are these 100 ants going towards a picnic, and they are moving first in a line of 100. And one wise ant realizes that that's going to take too long to reach where we're trying to go. So then they start going in 2 lines of 50 and thinking that they're going to get there sooner, which is true and wise. And then they have this epiphany again that how about 4 lines of 25 and then 5 lines of 20. And then finally, when you see this beautiful progression in the book, there reaches this point where they're like, okay, well, how about 10 lines of 10? And finally, what happens, which is a little sad, is that we've traveled way too slow and there's no food for us to eat, and you took so long with the rows. So it's a perfect segue into multiplication, into arrays, division, because these are inverses, rows, columns, equations, problem solving, working together, factors, and multiples. I think, Sari, if you want to just take on some of these hand raise, I just want to make sure there's no technical glitch, or if anybody, if people are not able to hear me at all.
Ma'am, it will be taken care of. You please
Sure.
carry on.
Okay, perfect. Thank you. And then Math Curse, one of my favorite books. And this one, I have had mixed responses from some of my math friends on this. Whenever we talk about this book, there's always that 50-50 sort of a response. There are some teachers who feel, educators who feel that this book is actually adding to math anxiety. I actually look at it very differently, but I'm going to give you a snapshot of the book a little bit. So a little bit. On Monday in math class, Mrs. Fibonacci says, she's a teacher, you know, you can think of almost everything as a math problem. And on Tuesday, I start having problems. So this is basically the main character of the book. And I feel the book is actually not about math anxiety and thinking about everything to be a problem, but to appreciate the math in everything. And one of those examples, a very beautiful example that comes in the book, is something that I would like to highlight, would be the following. I mean, firstly, what does the book do? And it talks about divisibility. It touches upon many topics. So this would be about 5th, 6th, 7th grade. Divisibility, fractions, time, conversions, inequality, sequences, money, life, binary. And here is that one little page in the book that I want to bring your attention to, which is, we are just about to go home when Rebecca, a student in the class, remembers the special birthday cupcakes her mom made. And there are 24 kids in the class. Rebecca has 24 cupcakes. So what's the problem? Rebecca wants Mrs. Fibonacci, the teacher, to have a cupcake too. Everyone is going crazy trying to figure out what fraction of a cupcake each person will get. And I'm the first to figure out the answer. Well, I've worked out some of the math here when we're talking about 24 cupcakes for 25 people, one including the teacher. Then if we scale it, we're looking at 96 out of 100, which means that each person will not be getting one cupcake, but 96 hundredths of the cupcake per person. So everyone should be sacrificing 4% of their share or 1/25 of their share to make sure that everybody has an equal share. Now, here is how problems are solved in real life. Thanks to our protagonist in the book, everyone believes me. I'll continue from where we stopped. I am the first to figure out the answer. I raised my hand and tell Mrs. Fibonacci I'm allergic to cupcakes. Everyone believes me and gets one cupcake. No one has to figure out fractions. And that's how we sometimes solve problems in life, because it's tedious. Who's going to cut? We have to rely on the artistry and cutting skills of people. And that one person who's going to get that 1/25 of that share, not 1/25, I'm sorry, what everybody has foregone, 1/25, yes. How is that person going to eat it, and all the complaints that that person is going to give, because everybody is getting a full share as opposed to this person who is getting a full share, but getting it in a very minuscule way. So this is how in real life sometimes we solve problems. Somebody sacrifices something, and then the solution is 24 cupcakes for 24 people. So some of these stories are such a beautiful way to introduce a problem concept in your class. And a lot of our young kids, our primary kids, I mean, I wouldn't say that our high school kids or our teachers, for example, don't like stories. We all love stories. But as our students progress, maybe they will not be so convinced listening to some of these stories as they are in high school, maybe. And that's when we bring in a lot more of history, math history into our classroom. Another good one, which is almost till 7th, 8th grade, I have used it for even actually for 9th grade for exponents. Another favorite book of mine is One Grain of Rice by Demi. And this is about a Raja in India, and who thinks he's always fair. And he's always collecting everybody's rice for storage, and saying that in case there's any famine, then I am the one who's going to be the provider. So if you're growing any rice, please give it to me. So he's collecting sacks and sacks of rice. And one day, there's a girl called Rani, and she basically, there was a bag of rice. I'm giving you a very gist version of the story, so please don't quote me on this. I have read it many years ago, and I have the book, but I was not able to find it in my library right now. I think I've given it to a student to read. So there's this girl Rani, and she basically sees a bag of rice torn, and some rice is falling down. So she actually goes and grabs it, and she wants to return it to the king. And when she does do that, she's asked by the king, "What reward do you want from me?" And actually, in retrospect, the king has at one point not been as wise and as fair and as just as he claimed to be, because there was a famine once and he did not share the rice with the villagers. So when this girl is going to give the rice back as a reward, he asks her, "What do you want as a reward?" And she says, "Well, today you will give me a single grain of rice. And then each day for 30 days, you will give me double the rice you gave me the day before." So she's explaining, so tomorrow you'll give me 2 grains of rice. The next day, you're going to give me 4 grains of rice, and so on for the next 30 days. And the king thinks that that's a very modest reward. And of course, he's promised it to her. So he grants it. And actually, as one can think of, we're all math people, it's exponential growth. So I'm going to actually skip through the the words here and take you straight through the math. So day 1, 2 to the power of 0, 1 grain of rice, and 2 to the power of 1, 2 grains of rice, and goes on. And I mean, you can actually get your students to even do these calculations using Excel and make it a technology lesson. And then eventually see what happens at the end of 30 days, where she basically gets all the rice back and more for the villagers to have their due, who have been so kindly been giving it and entrusting the king with their wealth. So it talks about fairness, it talks about wisdom, it talks about doubling, and of course, exponential growth. This is my segue sometimes to talk about compound interest. When we talk about compound interest, or I'm starting with exponents and properties of exponents, I use this story from literature. So if you want to find some more math stories, you may look up these resources, Math Through Stories or Mathical Books. These are some great resources to get at least an idea of the book and the theme and the age relevant. And then if you can, if you have a library that can give you access to these, or if you cannot find them, then find if you can, please invest in the physical copy. But if not, you may get into YouTube and look at some of the read alouds for these stories if they're available. So as I talk about my elder kids, as we're getting into our high schoolers and you know, who may not be convinced and may you know, as kids get older, as we get older, we always want that challenge. So so I segue my way into these kind of examples in my classes, where I bring in pop culture and I talk about some math fails. Math fails are basically my beautiful, you know, it's from life. I just try to get, you know, ways in which people have not used math correctly or efficiently, or they've made some mistake or error in their mathematical understanding of a concept, or just human error, and how that contributes to losses as well as, you know, sometimes life. So one is, this was floating around a lot during our, you know, pandemic, social distancing, and talking about, you know, it should be 6 feet apart, especially in the US. This was a thing about 6 feet apart, and there was this whole diagram right here on, you know, and you can clearly see it's a square. So it brings me to the Pythagorean theorem and talking about how it cannot be that this is 6 and this is 6 and this is 6. If I want my diagonal distance to be 6 feet, then I need to make sure that using Pythagorean theorem, if this value is x or any variable, and this is also x, then my x squares, my areas for these corresponding sides should be equal. The sum of that should be equal to the sum, should be equal to the area that's formed by the hypotenuse side. So basically, if I want to come to making my diagonal to be 6, which is 6 square would be 36, then there's no way that I can have a 6 and a 6 here to get that 36. It has to be, and then we'll have to do a little bit of algebra there. And I want to quickly work through that. So this is x and x. So I'm talking about x square plus x square being equal to 6 square. And that's my 2x square is equal to 36. And then I divide both sides by 2, inverse operations. So I'm basically looking at square root of 18. I'm going to neglect my negative value here, my negative root, because I'm talking about distance. And that is approximately 4.24, 4 and 24 hundredths feet. So math fail right here when this was actually published, put on, you know, on many bus stands, and right there, not a good use or good example for math, not a good day for math teachers. Another one is again a reality, NASA's Mars Climate Orbiter disaster, which is basically, the story goes as the following, that there was a Mars climate orbiter that was built at a cost of 125 million, and it was really heavy. This is in the year 1998, and it was made to study the Martian climate. And the navigation team at Jet Propulsion Lab used the metric system for its calculations, but Lockheed Martin in Denver, actually, which had designed and built the spacecraft, gave a crucial acceleration data in customary system of inches, feet, and pounds. And in a sense, for some time, the spacecraft was lost in translation due to this conversion error and the time lapse that it took for the people working under the team to actually figure out the difference in the metric versus customary system. So real, very real. And maybe for our high schoolers, these math fails would appeal more. And if that doesn't appeal them, then I talk about a lot of math history. Now, for a lot of my math teachers, sometimes when I go back to history, one of the arguments I get by teachers is, where's the time? I also sometimes get this, that, it's not in the syllabus though. It's, maybe you're talking about this particular proof and it's beautiful, it's elegant, but it's not in the syllabus. Here's what I have to say on that. It's going to be sad if our children go through K through 12 life and somewhere down the road, you have been their teacher and you do not make your student appreciate the beauty and the rationale behind a particular concept, even if it's one, and let them see that wow, that aha, that joyous moment. You've missed a golden opportunity just because under the pretext of saying that it's not in the syllabus. At some point of time, as I said, you will have an occasion, and sometimes to start and to settle your class in. And we talk about routines and everything in my next session on anxiety. But, sometimes just to begin your lesson, a little bit of history is good without just jumping right into the concept. And here's the formula and here's how we're going to use it. There are many other techniques to kind of really hook your students to the beauty of math. So I begin with my history. First, with kind of recounting what we did yesterday. We talked about your stories, my stories, our stories, and how those stories teach us how application of math is, how math is applied as of today. But our history is equally important because it tells us about the rationale, the origin, the proof of, when we have all these students who like enrichment, who like logic, and they do not want to be passed on just this is how we do it. So a lot of history helps us kind of bridge that gap and get our students to really appreciate where something is coming from. And I like to use actually story to make this really clear. So I am not a mythologist. I am not a historian, so please don't quote me on this. But I was speaking to an elderly person, and we were talking one day about how there's this superstition in India, especially, that we should not sweep or broom in the evening. And I had actually lost something, so I was really trying to get it. And I think my easiest way to do that was to broom and to sweep, and especially to broom and to try to get to find that. And that's when that elderly person told me that, Jaspreet, we don't do that. And like any immature math student, and my first question was why, I really need to do this, why? And there was no reply at that point. But I think at some point he went and thought about it, spoke to somebody, came back to me and told me, Jaspreet, one day, remember that happened, and I just want to tell you that there's a reason for that. It may not apply to life today, but the reason is that when we did not have electricity, when we didn't have light, if we used to sweep or broom in the night, in the evening when it's dark and dusky, actually a lot of wealth would leave. Let's say your earring fell down, a gold piece of jewelry fell down, and you actually swept it out in the evening without looking. So Lakshmi has actually gone out of the house. So that was the rationale at that point. Now, if I tell, why I use this story is that if I tell my child, my student, we don't do this, or this is not coming on the exam, or this is what you need to know. We always have this question in today's time, and we've actually encouraged our students to question why. And it's going to be kind of, we are not going to be doing them justice if we are not able to answer why. So history brings origin, history brings where it's all started from. So some of these timelines that I'm going to talk about, you may also be able to find on these websites, Mathagon and Story of Mathematics. Some of the ideas I'm going to talk about, I have actually come from a beautiful book that I read in my undergrad, which was John Stilwell's Mathematics and Its History. So it's a very fun read, and it's by Springer. So if anybody is interested in investing in this book for themselves, this is some of the history that I will touch upon in my next half today. So firstly, age of math. How old is math? I get a lot of this as a question. When did mathematicians literally think of these formulae, or like how did it begin? Well, how it began is age of math is as old as the age of humanity. And math has evolved from counting and measuring to complex and sometimes even abstract thoughts and concepts that we see in textbooks today. But it has traveled from, and that's why appreciating different cultures is very important. Of course, India has contributed a lot, but I also use an analogy a little later on how a lot of it's really been a global village where math ideas have traveled the world. So starting from Mesopotamia and Babylonian culture, and then moving into ancient Greece to China, India, and the Arabic world, and then back to Europe in the late Middle Ages, which is actually the European math is what we usually see in our textbooks pretty much today. So kudos to those who had ideas, but credit goes to those who made them accessible. And I just use the analogy of Facebook and Mark Zuckerberg for this, because as much as we may want to bash social media, if some of us are connected, it's because of social media. And maybe you and I have had these ideas, 20 years ago, decades ago, people may have thought about how to connect the world. But we have to give credit to those who actually proposed and actually implemented the idea and brought it to the world. So that's why a lot of times people talk about a lot of mathematicians from their own culture. We talk about a lot of Indians having already thought of so many ideas way before anybody had. But sometimes they were locked up. Sometimes they were in texts that in Sanskrit that nobody could read. And it was not brought forward. So thanks to printing press, and how you and I can actually read and understand these ideas. So the beauty, the elegance, and the joy and sophistication of some of these ideas I'm going to bring in now, which may not relate to my elementary and my middle school teachers, maybe, but I feel like anyone who is a math teacher should have some access and exposure to these, and I'm trying to do that in my next segment. So I always begin with Gauss, and is this beautiful anecdote, which is of back to the 1700s. There was a German schoolmaster, and he gave his class an assignment of summing the first 100 integers. His aim was to keep his kids quiet for some time, but one student came back with a solution sooner than expected. And guess what? That was this solution, which is basically sum of an arithmetic series, 1 to 100, and being equal to 1 to 100. And how did he figure that out? He had a deep insight. This was Gauss, by the way, the student. He had a deep insight that if you fold the series in the middle and then add in pairs, that means, let's go back. If I add the 1 and the 100, the 2 and the 99, the 3 and the 98, I will keep getting the sum of 101. And because I folded the series, I need to cut it into half. So that would mean that there are 50 such pairs. So if I multiply 50 with that sum that I'm getting every time, that is the sum of the first 1 to 100, the first 100 integers from 1 to 100. And this general formula today that we know as is the sum of the arithmetic series, which is n divided by 2, which is the number of numbers that we had, 100. We divide that by 2, which is 50. And then n plus 1 was my 100 plus 1, 101, which is what I was getting as the sum of the 1 and the 100, the 2 and the 99. And I usually tell this story sometimes to my middle schoolers as well. Usually when I've given them a piece of work, and you know, the idea is it's just for a lot of students, sometimes this may translate to that, you know what, and it's very beautifully put by Brian Hayes in The American Scientist, that on first hearing this fable, and I have had students tell me this, that most students surely want to imagine themselves in the role of Gauss. But sooner or later, all of us realize, most of us realize, that we are less distinguished than Gauss. And to get the right answer, it's usually a lot of hard work rather than native genius. And his hope, Brian Hayes' hope, is that the story could be told in a way that encourages those students to keep going. And perhaps it can be balanced by other stories showing that there's a place in mathematics for more than one kind of mind, which is when you want to bring in real life and also so many other mathematicians who have not always had these epiphanies. And that could be you and me, that could be artists from today and from centuries ago, but especially, you know, to connect it to the real world, artists of today who use geometry, homemakers who use economics and budgeting and finance in their home planning, engineers, of course, architects, doctors, scientists, people from our everyday walk of life that are using math in their work, in their existence. And of course, bankers, you know, people from finance, advertising, marketing, you name it. There is not a single person who is not using math at some level. So Gauss's story is a fun element, but of course, connecting it to how everybody could have some sort of a connect with math. And then it brings me to another mathematician, which is Pythagoras. Before I talk a little bit about Pythagoras, I do have to credit that actually the Pythagorean theorem appears almost 500 years ago already in an Indian text, which was Bodhyan Shulba Sutra, if I'm not wrong. And the Pythagorean theorem has been actually discovered independently by other cultures as well. But it was, again, credit it with proving the theorem and popularizing it does go to Euclid and Pythagoras. So what's the theorem? Sometimes I have some of my teachers ask me that, you know, we sometimes just give out the theorem. Can you give us like where it's coming from, what's happening? So, well, of course, everybody is familiar with the right triangle. And if I go back to history, where was this right triangle really in everyday life? The Bodhyan Shulba Sutra actually goes back to giving a lot of, it's a text that gives a lot of mathematical formulas for altars and fire pits in Vedic rituals. But if we talk about the Greeks, they some inspiration came from tying a rope, like an animal being tied to a rope, or a ladder that was placed. So that's why we see a lot of these ladder problems in trigonometry, or rope as one of the context for problem that uses the Pythagorean theorem. So what's the theorem? Everybody is a little familiar with that a square plus b square equals c square, but actually in Euclid's Elements, which is a book written in 300 BC, it is actually much more fundamental. Area is more fundamental than length. So we don't talk so much about the fact that we're talking about this leg of the right triangle and this leg of the right triangle, but the area that that particular side is able to create. So this is one area for one of the legs or sides, and this is another area. And we're trying to say that the sum of these two areas is equal to this. So the theorem goes like that in Euclid's Element, that a triangle is right angled if the sum of areas of the squares on the shorter sides, these are my shorter sides, equals the area of the square on the longer side. Now, where is the proof? So a lot of math, and the beauty of math is that we can prove it. So I've tried my best. This is for my elementary, my middle school, maybe even my high school teachers on how to prove the theorem. So we basically have a square, and I'm making a square within a square. There's a reason why I have used different colors for the sides, but I'm basically trying to put a square within a square. And I am naming these sections now because I get these 4 triangles, which I can also prove are similar. And I have my shorter sides, A, B, and the hypotenuse, the longest side here, which is C. And that's the case for this inside subscribed square. And I understand that the square's area is going to be C square, this colored one. And now I'm going to do a little bit of movement. The movement is going to be, and I'm going to show that transformation, that I am going to get my red and my pink to meet a little bit. So my red stays right here, but my pink shifts up a little bit and goes and sits there so that I can make a rectangle here. I'm just moving it. I'm just shifting it. And I am also going to be moving my green one down a little bit and shifting my blue to the right a little bit in a way that it sits perfectly like that. And when I do that, I'm actually able to see that these two short ones are actually the same as my A square, and that's my B square. And that's when I am able to prove that the sum of the squares of these shorter sides is equal to the square of the longest side, which is the hypotenuse. So there are many, many more stories and things coming from history. For example, quadratic equations. In fact, I know of a lot of textbooks that in fact don't say quadratic equation and say credit it to Sridhar Acharya. And then also contributions of Aryabhat, Brahmagupta, Padmanabh, and Bhaskar to kind of refine it to, like there were people contributing to make sure that the negative root was removed. So there's these small layers that were added, but essentially the quadratic equation, again, there is one element which we read off in school in our textbook, but in Sridhar Acharya's text, we actually see the proof slightly differently. So I'll talk about that. And I'll touch upon a little bit of these fractions and hieroglyphics. cannot go without telling a little bit about Rene Descartes and coordinate plane and how that came into existence. Again, maybe myth, maybe an urban legend, we are not sure, but that's what history is all about, right? It's been passed down from generations and generations. So yes, there are some ways in which these can all be validated, and sometimes it's just a story. So, and I talk about Zeno's paradox and how I use that to introduce calculus. So, quadratic equation, using what Sridhar Acharya has done, we start with a quadratic equation set up in a way that we are multiplying both sides of the equation with 4 times the coefficient of x square, which is a. So multiplying both sides by 4a, essentially. And that is going to make me use distributive property and open it out. And then I am, again, kind of maths with being logical, trying to make a perfect square trinomial. So add b square on both sides. Before I say this, I do have to pause. If I have my high school teachers here, I do have to say that this is a little different from completing the square, which is what I will talk about in my next slide. This is what has been done by Sridhar Acharya. So it's slightly different, but it's actually really cool. And I sometimes on a personal level feel it's simpler than teaching completing the square. So adding b square on both sides, because I am intuitive. I know I want a perfect square trinomial, which is going to be my 2ax plus b. That is me factoring out this left side of the equation. And then I want to basically start making it look at some point for solving for x. So if I want to solve for x, let me start by doing something to this side, which would mean taking square root so that it is not a square anymore. And then when the square root is taken out, then I want my b on the other side. So inverse operations, I'm subtracting b on both sides. I'm not showing that step. And then I want x alone. So I'm dividing by 2a on both sides. So I get somewhere very close to what we know of the quadratic formula, which is negative b plus minus. But we had actually, I think it was Padmanabh's contribution to eliminate the negative root, and because it was only being used in very real world examples. And so that negative root was something that was either not understood, not appreciated. So we do not see the plus minus part. But in today's textbook, in today's time, even if it's out of syllabus, whether it is there or not, completing the square looks something along these lines, where we have the quadratic equation, standard form. We start by dividing both sides by the coefficient of, again, x square, which is a. And then we are looking at trying to add, take something to the other side. So we are subtracting c over a on both sides, and then trying to make the left side a perfect square trinomial. And there's, a lot of times when this has been taught, there's no relevance sometimes to this b over 2a, or a negative b over 2a rather. So rather than going into the math, which I have already shown here, I want to talk about relevance of doing this or teaching this to our children. Well, one is beautifully how it progresses and gives me the quadratic formula, gives me the value for my roots. But also to understand that what does the b square minus 4ac, which is known as a discriminant, or what does my negative b over 2a really do? So I show this using Desmus, a graphing calculator app, totally free. I have put in 3 quadratic equations, and look how beautifully just changing the constant is showing me these different graphs. So the blue one corresponds to this one, which shows me 2 roots. So the discriminant, that b square minus 4ac, is actually telling us which way, how the parabola is going to intersect the x-axis, and whether I'm going to have 2 solutions, 1 solution, or no solution. When I'm talking about solutions or roots, I'm talking about how you can see it actually visually, how this parabola, which is opening upwards, is intersecting the x-axis. I'm seeing those x-intercepts right here at 1 and at 3. But for this equation, x squared minus 4x plus 4, I am actually seeing my discriminant is actually equal to 0. So I only see one solution. And here for the green one, I actually get imaginary roots where I am seeing that it's not touching the x-axis. So even the negative b over 2a has relevance. It's basically where the vertex comes from. And the vertex is telling you where the quadratic function is going to be minimum or maximum. Now, this may not be relevant to students as you teach them, but when you talk to them about this game called Angry Birds, and where they have to shoot and get the bird to come there, shoot a stone for I'm forgetting now, I've played this long back, but even like throwing a ball in the air, or, anything that uses, that mimics a parabola, we are looking at finding these things. And for that, all of these applications are needed, and they have a rationale. They have this very important rationale. So where am I getting those vertexes, x and y coordinates from? The negative b over 2a is the x value. The y value is the negative of the discriminant over 4a. So a lot of this, again, story of maths, this is my figure from here is from the story of maths. You may also, as teachers, if you teach high school, or just for the fun of it, visit and see some of these beautiful connections. When I talk about fractions, fractional notation was used by ancient Babylonians and Greeks, but the oldest known system that we see is in Egyptian notation. So again, anybody wants to try this out, you can. In Egyptian numeral hieroglyphics, there was this symbol for each and every number, and they thought about, their number system was base 10. So it was 1, 10, 100, and so on. So what number do you think we're trying to represent here? I don't think I have the chat open, but maybe I can take that very soon when I'm talking, doing my Q&A. Or let me just give it out. I have some hands up now, but I'm sorry. Sergio, maybe if you can open the chat really quickly for a minute.
Okay, ma'am.
Thank you.
I have opened it.
Thank you. So we have some teachers. We have, okay, thank you. 276, right? 276, not 96, because here we have my 200s and my 710s right here, and my 6 ones. So fractions and hieroglyphics is one of the ways in which I actually begin fractions with the 6th grade, I would say. And also representation and how beautifully history plays a role in how we see it as of today, and what even like how unit fractions were being used as early as when Egyptians started using them, and all those debates on whether it's true, whether it's not, and what people have thought through history. So we have so many of these stories, and I would love to be able to mathematize all of you for these, but I'm looking at the time, Saryu, so let me know if I can move on, or we should pause for questions.
You can take up a couple of questions, ma'am.
All right, perfect. I just wanted to tell this very sweet, short and sweet story about Rene Descartes and the coordinate plane. And the story goes like this, that Descartes, this French mathematician, was once lying in his bed and saw a fly on the ceiling above him. And as he watched the fly, he thought about how the fly's location could be described using the edges of the room for reference. And this is our starting point sometimes for me when I'm starting the coordinate plane. And the Cartesian coordinate plane, which kind of brings us to, the a segue for anything that we do as high as calculus in high school. So Zeno's paradox is something I wanted to discuss, which is a beautiful one, but maybe if not today, I will be happy to take this up in my other sessions with all of you. So I am going to pause here and take up any questions that anyone may have. Sadhu, if you want to leave it open for anyone to ask anything.
Yeah, any more questions? Teachers, you can ask in the chat box. I have opened the chat box. Let's see. I think we have a hand raised from Sunita Sharma, ma'am.
Yes, for a long time.
Yeah, for a long time. So I'll ask Sunita, ma'am, to unmute yourself.
Yes, ma'am, there was no voice. That's why I have raised the hand, ma'am.
Sunita, I hope you were able to hear after.
Yeah. After that, yes. But I can't communicate to you. That's why.
All right.
Yeah, sure.
Okay. Thank you, ma'am.
Thank you. We have someone asking us, how can we teach students using poetry? Well, one of the most fun exercises I've had, of course, I mean, you can Google it, maths using poetry. We have a lot of teachers sometimes who are poets themselves, and they use math, and you'll always find some sort of a math rap, math poetry always happening. But one of an assignments that I had my 6th graders do once, which was a beautiful assignment, was the digits of pi. Use the digits of pi, but make a math poem for, like, so if it's 3.14, I'll just give an example. So using as many as the digits as you want, but in that order. Make a 3-letter word, and then a 1-letter word, and then a 4-letter word, and then a 2-letter word. So it was a beautiful way to get them to memorize the digits of pi, but they made a poem or a story using the digits of pi. So that's that. But there's so much out there. There are so many beautiful, as I said, I am only able to touch the handful of the beautiful literature and history that's out there that connects our math and works with them. But when we're talking about somebody asking us, can you suggest some books on interesting facts? The history of mathematicians, I need to go back. That it's called, I actually mentioned it. This was from my undergrad. I'm sure there are many more out there. But there's actually also a course, if I'm not wrong, taught in Australia on the history of mathematics online, and it's free. So the book that I studied from is known as Mathematics and Its History by John Stilwell, and that would be a great resource to actually invest in. Any other questions, anyone? Thank you for your wonderful feedback, everyone. Thank you for your patience. Sadhu, I will get you to take over now.
All right. Thank you so much, Jaspreet ma'am, for such a lovely session.
Thank you.
All the stories were simply amazing, and the way you connected the progression of concept through the stories, especially. Personally, the ones I liked are 1 grain of rice and the Mars climate orbiter, right? And this one, the last thing that you touched on was fractions and hieroglyphics, right?
Yes.
I'm sure each one of you have your own takeaways. Thank you, Jaspreet ma'am, and we are looking forward to other sessions next week also. Now, to all the participants, before we sign off, teachers, I would like to remind you all that our next 4 sessions are scheduled on 12th May, 13th May, 19th and 20th May. And at the end of maths webinar, that is on 20th May, there will be a quiz for all of you. So please try to attend all the 6 sessions. Thank you all for being a part of this session. Till next week, thank you so much. Have a good weekend. Thank you, Jaspreet ma'am.
Thank you so much. Thank you.